Hello and welcome back to Lesson 2 of our Ecological Design Modeling series. In our previous lesson we were looking at having a pond of algae, and we're interested in how much algae is going to be there at any point in time. Maybe we want to know how much algae is going to be there tomorrow or next week or maybe next month. And we can see that this balance of algae, the amount of algae that we have, is a balance between the amount of growth of algae, new algae that's created and stored in the lake, and the death of algae or the loss of algae. So we have a storage of algae and two flows, an inflow of growth and an outflow of death. And this becomes the basic premise for the types of modeling that we will be doing in here, where we have stocks and flows. So we have flows and we have stocks, or sometimes called rates and states. These are the two basic components of our systems models. So in our case, we would have a storage of algae. This is our storage symbol. We're using the energy system symbols. So this is a storage, or a stock of algae, if you will, in this example. And we have an inflow, and we have an outflow. So in our example with algae in the pond, growth is the inflow, death is the outflow. And what we can see is that the amount of algae, or the amount of storage that we have at any point in time, is the balance between what we had previously plus any new material that comes as inflow minus any material that leaves as outflow. So the basic premise is that the amount of storage, or the change in storage, is just a balance between inflow and outflow. So we can say that the change in storage equals inflow minus outflow. A good example of something that we could represent with this model would be your bank account. You have a storage of money in your bank account, and you have inflows of money into your bank account, and you have outflows from your bank account. You have deposits and withdrawals. And the amount of money that you have tomorrow is going to be how much money you had today plus any deposits minus any withdrawals. And so one of the things we need to add to this equation here that we've written is that the change in storage is actually the change per unit of change in time. So our next step then is to turn this into a differential equation, or a difference equation. So we're going to symbolize our inflows with J for flows, and give it a subscript of I to indicate inflow. And our outflow will also symbolize with a J, but we'll give it a subscript of O for outflow. And then we have our storage represented by Q. So now we can use notation to rewrite our word equation here, so that the small change, lowercase d, per change in time, dq dt, equals ji minus jo. Well, this is not very interesting at this point because we haven't defined what ji and jo equal. So often what you'll find is that we can assume what are called first order kinetics. Related to how much flow comes from a storage. So Jo is going to say that the flow JO is proportional to Q. So we're going to symbolize that with an equation. JO equals K Q. And this K, we'll call it a pathway coefficient. And it's a constant. And it means, in this case, that the flow JO, the outflow, is going to be a constant proportion of how much we have in Q. So if we go to our algae example, where outflow represents death, what we're saying is that depending on how much algae we have, represented by Q, a certain proportion of that algae is going to die each unit of time. And that proportion is not going to change throughout our simulation. K is constant. So now we can substitute our KQ in for J sub, and we'll have that JI minus KQ. And now we can see that the change in Q is proportional, is affected by how much is in Q through the outflow. Our next step is to take the equation for the change in Q, which we have here, dQ dt, and add it to the previous value of Q, or the old value of Q, so that we can determine what the new value of Q is. So I'm going to write that up here. So the new Q equals old Q plus the change in Q. And this we could solve here. dQ equals Ji minus KQ, and we need to multiply all that times dt. And this becomes what we substitute in this equation. So eventually what we'll have is we'll have multiple storages, we could have multiple flows, and we could have more complicated equations than just KQ that will tell us what dQ is. In this simple model, tank with one storage and two flows, dQ is fairly straightforward. We can rewrite this equation as the value of Q at some time t plus our small change in time dt, which is the same dt down here. This is called our time step. Equals the previous value of Q, which was a t, plus dQ. And this is the equation we'll be using in our spreadsheet software.